Welcome to our review on the Haber process. So what I've given you here first of all is a diagram of the equipment used to carry out the Haber process as a whole. On the left hand side we can see where our two raw materials enter, which are nitrogen and hydrogen gas. They're put under a high pressure first of all, and then they're pumped into the reaction vessel, which has a temperature of 450 degrees Celsius, and it's got these beds of iron catalyst scattered throughout. As it passes through there, it's going to convert that nitrogen and hydrogen into ammonia, and then as it passes out the bottom of our reaction vessel, we've got a cooling area where we then collect the liquid ammonia, and then the other gases which are unreacted get pumped back in. So when we're looking at the Haber process, we need to remember the actual conditions chosen for this reaction. So 450 degrees Celsius is the temperature, 200 atmospheres of pressure, and an iron catalyst. So by doing that, we're going to get a yield of approximately 30%. One of the favourite questions that they like to put onto your exam paper is talking about the conditions involved in the Haber process. And quite often they will use this graph here, which on a first glance looks a little bit daunting, and some of you may think I can just turn the page and ignore it. Don't, it's not that bad. On our x-axis first of all, we've got the pressure. So all we can see is it increases as you go from the left to the right. On the y-axis, the vertical one there, we've got the percentage yield of ammonia, so the amount of ammonia we're making. And then those four coloured lines on the graph are different temperatures, and you can see which temperature on the side there. So if they were to ask you about what temperature to use for this, just looking at the graph, the best temperature would actually be 200 degrees Celsius, because if we look, the lines, as you increase the temperature, are actually producing less yield of ammonia. So that 500 degrees Celsius line is right down and only makes about 30%, whereas 200 degrees Celsius makes 90 something percent. Now what we can actually work out from that is that our forward reaction is exothermic and the backward reaction is endothermic. And the reason that we know that is that when we increase the temperature, the equilibrium position is moved to the left, which therefore decreases the yield of our ammonia because it's in the direction of the endothermic reaction. So what we then have to do is work out the compromise between the yield and the rate of the reaction. Because if you remember, the lower the temperature, the higher the yield will be, but the higher the temperature, the faster the rate of reaction will be. So to get the balance between them, they've chosen the temperature of 450 degrees Celsius because it gives quite a good yield, but also quite a good rate of reaction. The second condition is the pressure. So I've given you the balance symbol equation for our Haber process there. And if we think back to the work we've done on equilibrium, we know that if we increase the pressure, then the equilibrium position is going to move to the right because there are fewer moles of gas on the right. So that means that if we increase the pressure, we're increasing our yield of ammonia. But again, we need to think about the compromise here, because when we have very high pressures, we've got the concerns over safety and also the issue of the higher cost of equipment in order to generate those high pressures and withstand them. So we come up with a compromise of about 200 atmospheres there because it gives a high yield without those very high costs and risks. The last thing to consider is the fact that we're actually carrying out a recycling process in this. Because what we have, as those gases leave our reaction vessel, then it goes into that cooling area. So what we find, ammonia will condense to a liquid before hydrogen or nitrogen do. So as it passes through the cooling area, what happens is the ammonia condenses to a liquid, which can be collected in the tank at the bottom and just run off. But the nitrogen and hydrogen, which haven't reacted, are then remaining as a gas. So we can just pump those straight back into the reaction vessel, And what that means is that we get an overall yield of about 97%. Hopefully at the end of this video you can now recall the conditions that we choose for the Haber process: 200 atmospheres, 450 degrees Celsius, iron catalyst. You can explain why we use those and not other temperatures and pressures which may be better. And you can also interpret graphs involving yields and different reaction conditions.